Welcome to videos on linear integrated circuits. In this video, we shall see two-stage op-amp consideration. So we'll consider the basics of design of a two-stage op-amp and what are the constituents of a two-stage op-amp. So this is the circuit diagram of a two-stage op-amp, where the first stage happens to be an active load differential amplifier constituted by M1, M2, M3, M4. M5 is the MOSFET which provides the required bias current for this differential amplifier, and we have a CS amplifier which is represented by M6 and M7. We have V0 dash as the output, single end output of the differential amplifier, with plus and minus as the terminals for a differential input of a differential amplifier, and we have the final output voltage as V0 of the two-stage op-amp. And we are considering R1 and C1 as the output resistance and the output capacitance of the first stage, and R2 and C2 as the output resistance and output capacitance of the second stage respectively. So let us see the AC equivalent circuit of that two-stage amplifier. So we know that this is the representation of the transconductance of the differential amplifier, which is GM1 into V in the current source representing the transconductance of differential amplifier, and we have the R1, the representation of R out of the first stage. This is C out of the first stage. Similarly, GM2 happens to be the transconductance of the second stage CS amplifier, and we know dash is the input to the second stage, which happens to be the output of the first stage, and R2 and C2 happens to be the output resistance and output capacitance of second stage. So that's what is written here. R1 happens to be R out of stage 1, C1 is C out of stage 1, R2 is R out of stage 2, and C2 is C out of stage 2. And we have tau1, which is a time constant corresponding to first stage as R1 C1, and corresponding to second stage is R2 C2. And we know that the R out of the first stage, so from this we know that the R out, that is represented as R1, is R02 in parallel with R04. Similarly, R2, the output impedance of the second stage, happens to be R06 in parallel with R07. So that's what is represented here. And we know that this is how the circuit diagram can be represented in the form of a block diagram. So we have the first stage having a gain of A1, and this is the second stage having a gain of A2, and we have the pole representation of this in terms of its time constant, and second stage is also represented by a pole having a time constant, which is represented here. Now we can see this is the differential amplifier stage, this is the CS amplifier stage. Let's assume that differential amplifier stage, which we consider as first stage, has got a gain of A1, and as a pole at with a time constant tau1, it is 1 plus S into tau1 happens to be the representation of the pole. And similarly for a CS amplifier, we have A2 as the gain of the CS amplifier, and we have a pole with a time constant tau2. So this is the A1, which happens to be GM1 into I1, GM1 of the first stage multiplied by the R out of the first stage. GM of the first stage happens to be GM, and the R02 in parallel with R04 is the R out of the first stage. And similarly, for the second stage, so we can write it as GM of the second stage and R out of the second stage. And if we just go back and see the circuit, so R out, the GM of the second stage is contributed by this M6. So that is GM6 multiplied by the R out. So R out is actually R06 in parallel with R07. So we can also write, since it is parallel combination, we can write it as 1 over the conductance, the admittance of R04 and R02. So we have the expression for the gain of first stage and second stage and their pole positions at with a time constant tau1 and tau2. So this is the block diagram representation of the two-stage op-amp. Now we can write the overall transfer function like V naught by VID given by the product of those two blocks, that is A1 into A2 divided by 1 plus S tau 1 into 1 plus tau S2. So which we can write it this way. Now we can clearly know the location of the poles, the first pole which we name it as P1 dash, as its S-plane representation, its S-plane position will be minus 1 over tau 1. So that's what we are representing. This we are representing P1 dash as the pole of the first stage and P2 dash as the pole of the second stage, which is located on the S-plane at minus 1 over tau 2. And we can know the corresponding frequency of the first pole as omega P1 dash and the second pole as omega P2 dash. Now we know that the initial, if you write the Bode plot for this particular, so we can write it as 0 dB till the first pole comes. So once the first pole comes, the slope is minus 20 dB per decade. So once we have a second pole is also introduced, so we'll have an overall slope of minus 40 dB per decade, and it crosses 0 dB, so which we name it as gain bandwidth product, which happens to be omega GC here. This is the gain crossover frequency. And here we are writing the phase angle of minus of A beta. So since it is minus of A beta, we are writing it as 180 degree here and it is 0 degree. And wherever this, of course, we will just talk about this in the coming slides. Okay, why we have taken it as 180 degree. And you can see whenever it crosses the 0 dB line, this happens to be omega GC. Omega GC, we are dropping a line here. The corresponding phase at omega is equal to omega GC with respect to 0 happens to be the phase margin. Now the phase margin of the first two-stage amplifier happens to be less than 10 degrees, so which is very small. Let us see the effect of this small phase margin for this two-stage op-amp. So what is the effect of this? Of course, we were talking about this is the actual transfer function we want to have. This is the magnitude plot 0. Now here at omega is equal to omega p1 dash, it makes a slope of minus 20 and it is again minus 40 dB. This is omega gc. And if you actually plot the magnitude which is the actual phase, that is A into beta, since we have two circuits which are both are inverting, so we will actually end up with, now we can see this is, so we're going to have minus 180 degree line. So this is A beta. Usually we write in Bode plot. So this is 0 degree, this is minus 180 degree. Wherever it crosses omega gc from minus 180 degree, what is this phase? This is known as phase margin. So what we'll do is we'll simply add 180 degree to all the y-axis values. Now when I add 180 to 0 degree, this will become 180 degree. When I add minus 180 degree to uh, when I add plus 180 degree to that minus 180 degree, this will become 0 degree. So instead of measuring the phase margin from minus 180 degree and this omega gc point, suppose if you are plotting this as a phase of minus a beta, so whatever the phase difference from 0 degree to this phi of omega gc happens to be the phase margin. So instead of plotting it from 0 to minus 180, if you plot it from 80 to 0, so here the difference was from minus 180 to this point. Now it is 0 to this point. So there is no change in the magnitude of any of the phase margin. So these two are identical plots, but only thing is that the reference has been changed from 0 to 180 degree and this minus 180 degree to 0 degree. The phase margin is the deviation from 0 to this phi of omega gc, but here it is the difference from minus 180 degree to this point. So the phase margin still remains the same. Now as we can see, now the phase margin is very less. So now since the phase margin is very less, so what is the effect of that phase margin on the settling time? Now we can see this graph shows the time response of a system having different phase margins. Now you can see this is the phase margin of 45 degree. So it has got more ripple, the MP is more, the maximum overshoot is more. When the phase margin increases to 50 degree, now it has slightly reduced. When it is 55 degree, it is further reduced. I can see at around 70 degrees, 65 degree, is the phase margin. Now we're going to have a reduced overshoot. When the overshoot is reduced, now we can see it will settle down sooner to that desired value. So settling time is purely depending on what is the phase margin of the system. If the phase margin of the system is less, we're going to have larger settling time. So op-amp takes larger time to settle down to the desired output if the phase margin is less. So it is designed to have a greater phase margin so that it will have a lesser settling time. So phase margin and settling time are interrelated. If the phase margin is more, then the settling time is less. So we need to have the op-amps to be designed such that the settling time should be as small as possible so that it will settle down very soon. So that requires a larger phase margin. But in the previous two-stage op-amp, we found that the phase margin is very, very small, like okay, 10 degree. So that results in a very uh, large settling time. So we are supposed to now improve the phase margin so that we can reduce the settling time. So now the phase margin, which is related to now zeta now, because now zeta purely depend zeta will decide what your MP. If the value of zeta is small, the maximum overshoot is more. So you can see now we have a phase margin which is 45 degree. We have a larger MP, so that zeta is smaller now. So for the required phase margin, now we can find out what is the value of zeta. So if the phase margin is small, then zeta is small, so settling time is more. So in order to reduce the settling time, zeta should be increased. That is, we need to increase the phase margin. So in order to increase the phase margin, what we need to do is we need to compensate the two-stage amplifier, two-stage op-amp. So next is we need to have a compensation circuit to increase the phase margin of a second order two-stage op-amp. Now this is a two-stage op-amp with a Miller compensation. You can see it is just exactly the same circuit from the previous one. Only thing is that we have added a capacitor CC from output to this point. This is known as the Miller compensation capacitor. The purpose of using this compensation capacitor is to increase the phase margin, which will reduce the settling time, which is what is desired. So with the introduction of this compensation capacitor, so our aim is to reduce the settling time. So settling time can be reduced by increasing the phase margin. So let us see the effect of this introduction of compensation capacitance, which is also called as Miller compensation capacitor. What is its effects on the system response? Now just have a look at this. So this is the effect of Miller compensation. We had the earlier poles, that is P1 dash and P2 dash. So these are the open loop poles when CC is equal to 0. What do you mean by CC is equal to 0? When we not provided any compensation. So we had only two poles, which is P1 dash and P2 dash. So what we discussed in the previous slides, you can see now this is P1 dash and P2 dash. So we had poles P1 dash and P2 dash without any compensation when CC is 0. Suppose if CC is non-zero. Now we can see we have a CC which is non-zero here. So now this pole which was there at P1 dash has now moved to P1. The pole which was there at P2 dash has now moved to P2. So there is a pole movement happening from this P2, it is moving further towards the left side, whereas the P1 dash is coming closer to the imaginary axis. So this is an effect of Miller compensation. As the value of CC is non-zero, the pole which is close to the imaginary axis will further move close to the imaginary axis. The pole which is away from the imaginary axis, it tries to move further away from the imaginary axis. And one more important phenomenon is there was no zero in the previous transfer function. So upon introduction of the Miller compensation capacitor, the zero which was at infinity will become now finite. Now you can see we have a zero being introduced onto the right hand side of the plane. So this zero will be introduced whenever we do a Miller compensation. So this is the effect of Miller compensation on the circuit S-plane representation. And its corresponding Bode plot will be, now we can see that dotted one is the uncompensated. We had a pole at omega P1 dash, omega P2 dash, we had the slopes minus 20, minus 40. and of course you can see there is a GB. Now we'll see